Hello everyone, myself Yadagiri. I am the faculty of Basic Electrical Engineering, MLR Institute of Technology, Hyderabad. So in this session, we are going to discuss about the network, different types of network theorems, and also we need to briefing about the superposition theorem. So actually, the network theorems are used to apply the all kinds of complex circuit to get the response within the short time. Means all kinds of network theorems are used to apply for the complex networks to get the response quickly. That is the purpose of the network theorems. So there are the different types of network theorems are there. So the first one is superposition theorem, and the second one is Thevenin's theorem, and the third one is Norton's theorem. And fourth one is maximum power transfer theorem. So these four theorems are we are going to discuss. And these four theorems are used to apply for any kind of complex circuits to get the response within a short time. So this the maximum power transfer theorem. So now let us go to discuss about the superposition theorem. So in this complete session we need to discuss about the entire superposition theorem. So what does it mean by superposition theorem? And what kind of prerequisites are required for this kind of superposition theorem, and also so what kind of procedure are required to apply the superposition theorem for any kind of complex circuits, and also the how to do the problems or how to deal the numericals based on the superposition theorem. So these so many things we have discussed in this entire session. So let us go with the superposition theorem. So it is a network theorem. It is also used to apply the complex circuit to get the response quickly. So it states that it is a network theorem. So it is applicable for any kind of network having the two different types of independent sources. I mean, it is stated that in any linear bilateral active network consisting of the two or more than two independent sources. So the response of any one of the branch is equal to the responses caused by individual sources. I mean to say, the response of any one of the branch is equals to the algebraic sum of responses caused by individual sources, and the remaining sources can be replaced by their internal resistance. That is the statement of superposition theorem. So simply the superposition theorem is stated that in any kind of linear bilateral two-terminal active network, so consisting of two or more than two independent sources, the response of any one of the branch is equals to the algebraic sum of the responses caused by individual sources, while rest of the sources can be replaced by their internal resistance. So if it is a any kind of internal resistance having this kind of source, we can simply replace it by that source. I mean, what I want to say means, so we need to take this kind of two source network, that is a V1 source, other one is a V2 source. So we need to get the response at this point, I mean at these elements. So to calculate the response of this particular element by applying these two sources, so first we need to get the response by this source, and also we need to get the response by this source. After that we need to add the two responses. So that is the total response of this corresponding element. So that is superposition theorem is stating us. I mean superposition theorem is saying us. So the response of any one of the branch is equals to the responses given by the individual sources, while rest of the sources can be replaced by their internal resistance. While connecting this source, the other source can be disconnected, means which can be replaced by their internal resistance. So if it is a voltage source, so let us say this kind of source is a voltage source, so we can simply replace it by short circuit path. Means if there is no internal resistance of this source, so we need to replace with the short circuit path. So if the network having the in the independent voltage source, we can simply replace with that corresponding source as the short circuit path. And if it is a the energy source as a current source, we can simply replace it by an open circuit. This open circuit. So in the network, we need to connect one source. So the corresponding remaining sources are the corresponding source is a voltage source. So we can calculate the required values or required the parameters based on that one, and the rest of the sources, that is a voltage source, we can simply replace it by their internal resistance. If it is not there, we can simply replace it by their open short circuit path. So if it is a current source as a energy source in the network, that is we can simply replace it by open circuit path. So this is the statement of the superposition theorem. The superposition theorem is simply states that in any linear bilateral two-terminal network consisting of the two or more than two independent sources. So the response of any one of the branch equal to the responses, algebraic sum of responses caused by individual sources, while rest of the sources can be replaced by their internal resistance. So that is the statement of the superposition theorem. If the alternate source means if it is connecting this source and the while rest of sources can be disconnected. If it is a voltage source, we can simply short circuited. If it is a current source, we can simply open circuit. So this is the statement of the superposition theorem. So now let us discuss about the explanation about the superposition theorem. So now need to take this same circuit here. So now we need to take the step number 1, that is apply the V1 source to the circuit and the remaining source or other alternate source can be disconnected. So here there is a voltage source. That voltage source can be simply replaced by short circuit because there is no internal resistance of that source. So we can simply replace it by the short circuit path. So now need to get the response of each element while connecting this source. So first of all we need to find out the total current of circuit, then only we'll get the current through each resistor I1, I2 and I3 values. So in this step we need to discuss about the current through each resistor. So while connecting, the V1 is acting alone. The source 1 is connecting to the circuit there independently. That's why. So we need to apply the Ohm's law to entire network. Then we will get the response of the each and every element. So according to the Ohm's law, the current equal to the V by R. So the total current of circuit equal to the I total equal to the V total upon R equivalent. So here V total is given in the question, in the example, that is a V1 only, V total is a V1 only. Then the other one is a R equivalent value. R equivalent value we need to find out by using this. So the different kinds of elements. So the equivalent distance of this kind of source. So this is R equivalent equal to. So based on the current division, so the R2 and R3 are parallel, which in series to R1 resistor. So here R2 parallel to R3, which in series to R1 resistance. Hence the whole equivalent value of the above combination is R2 into R3 by R2 plus R3. So plus R1 capacitors. So this is a way to get the R equivalent of the above circuit, so that we will get the, so IT dash means total current while connecting source 1. The source 1 is acting alone, that is called IT dash. So that is a VT upon R equivalent dash. VT upon R equivalent dash. So this dash will indicating us the, so the source 1 is acting alone to the circuit. That's why we need to consider the total dash, R equivalent dash. So this is a way to get the I total of the circuit. Then after that we need to find out the current through each resistor. So the current through each resistor means the current through first element, current to value of R1. So that we have given already, the name is I1. So this I1 equal to the I total dash equal to same. Both currents are same because, so whatever the current given by the source, that is a I total dash is same as I1 current. That's why both are equal. And other one, how to get the current through the remaining two elements means we can apply the current to division rule. Then apply current to division rule. So according to the current division rule, the current through the R2 element. So current through R2 element. So that is I2 equal to, total current of circuit into, according to the formula, total current of circuit into, so we can take it as a opposite resistance. So this we have already done in the earlier sessions. So based on that we can apply the current division rule here to get the response of this element. So divide by the total resistance. So here I total is this one only. The opposite resistance of this corresponding branch is a R3. So that we can take it as R3 in the numerator and divide by the total resistance value is only we can consider the combination of these two. Whatever the elements are participated in the division, we need to take the combination of that is a total resistance. So that is R2 plus R3. So this is the way to get the I2 value, current through the second element value. So we have given the name as a I total dash, and also we can say I1 dash, and here also we can take it as a notation as I2 dash, and here I2 dash, here also I2 dash. So it is this dash term indicating us the source 1 is acting alone. So the corresponding current through this particular element is the I2 dash equal to total current of circuit into opposite resistance upon the total resistance. So then alternate element, so that is I3 dash equal to, current flows through the R3 element is the I3 dash equal to same as total current of circuit into, that is I total dash into, here also dash we got. So then opposite resistance, similar to the previous, opposite resistance by total resistance. Here opposite resistance upon total resistance. So here I total dash keep as it is. If it is a real number value, if we need to solve any kind of real term question, then we can simply replace with the corresponding value. So here we have considered only the notation, that's why the I total dash keep as it is, and instead of opposite resistance, so while considering this particular element, and the opposite element is the R2, so that the R2 is opposite resistance upon total resistance is again R2 plus R3. So this is I3 dash. This is the I1 dash value, and this is the I2 dash value, I1 dash, I2 dash, then I3 dash value. These three values are, so current flows through the network, through the each and every element, while source 1 is acting alone. So in the entire step number 1, we are discussing about the current through the each and every element. So before going to that, we need to disconnect the remaining elements in the network, remaining sources in the network. So here in this step, we have got the only two sources. So one source disconnected, and which is replaced by their short circuit path, because there is no interactions of that source. Then we can simply replace it by a short circuit path. So this is the corresponding network, and this is the current of the total network, and the current flowing through the R1, and also the current value of R2 and R3. So this is the step number 1. In the step number 2, so that is the step number 2. The step number 2 means, so we need to disconnect the previous source and connecting the other sources. So whatever the sources are present in the network, so then we can connect that source, and the remaining sources are disconnected. So previously here there will be a voltage source. So that voltage source can be deactivated, and which can simply replace it by the short circuit paths. Similar to the previous case. And we need to find out again the response of the each element while connecting the source number 2. So that corresponding current of the network is VI equal to V by R according to Ohm's law. First we need to find out the total current of circuit, that is IT dash equal to, IT equal to VT upon R equivalent, we can say. So the source is acting alone, that's why IT double dash we can keep, and here we got the VT double dash, and here we got the R equivalent double dash. So previously here we got the VT dash and R equivalent dash, and I1 dash, I2 dash, and also the I3 dash. Here we can consider the notation as IT double dash, VT double dash, then R equivalent double dash. Here VT double dash, total voltage of the network is given according to the source value, and the R equivalent double dash we need to find. So R equivalent double dash we will find out based on the current flow of the network. The current given by this source is IT double dash, so which circulating towards the R3 and enter here, divide between these two. So based on this one, R1 and R2s are in parallel, which in series to the R3. R equivalent of the above network is R1 parallel to R2, and which combination is in series to R3. So we can simply elaborate this term. We will get R1 into R2 upon then R1 plus R2 plus R3 we can get directly. So this is R equivalent double dash value. The R equivalent of the whole network should be R equivalent double dash equal to R1 into R2 by R1 plus R2 plus R3. So this is the corresponding equivalent resistance value of this network. And after that we need to find out the current through each resistor. First, this is the first element, foremost element, which is near to the, which is in series to the source 2. So that first we need to find out the current flows through the R3 element. So we have already given the name as, that is I1, here I1 double dash. Previously we have given the, so this is I3. So I3 dash, like I3 dash and I2 dash, here are I1 dash. So this time we need to give, so the same only here I3 double dash So this one we given the name as a I2 double dash. It is I2 double dash, and this corresponding current is I1 double dash. This is already we have given the names previously. That's why it is I1 double dash, I2 double dash, then I3 double dash. So need to find out the I3 double dash value. I3 double dash equal to the, so the whatever the current given by the source, that is also same as the R3 current. That's why it is IT double dash. Then remaining elements. So that is current through R2 and current through R2 and R3 elements. So the first we need to find out the current through R2 element. So we are applying the from current to division rule, or we are applying the current division rule. So according to that one, I2 double dash equal to the total current of circuit into opposite resistance of this one, that is R1 in this case. So divide by R1 plus R2. So there is the total resistance of the circuit. This is the I2 double dash value. Then similarly find out the current through R3 element, that is a I3 double dash. I3 double dash equal to, second to the current division rule, that is the total current of the circuit into again opposite resistance of this corresponding branch, that is, so this R2. So the opposite resistance is R2 upon total resistance, that is R1 plus R2. So this is the current through each and every resistor. So this is a R3 resistor value is I3 double dash. So this is the R2 resistor value is the I2 double dash, and the R1 resistor is it is a R1. The R1 resistor is so that is I3 double dash. So this is the case. So we need to analyze the current through each and every resistor. So this is R1, R2, R3 previous case. So here also this is the R1, this is the R1 and R2, R3 value. So the corresponding current is so we already given the name as this is the I1 and this is the I2 and this is the I3. So similarly, so here also we need to give the name as it is the I3 dash, and this is the I2 dash, and this is the I1 double dash. So this is I1 double dash, I1 double dash, I2 double dash, then I3 double dash. The current through R1 is a I1 double dash. So current through R2 is a I2 double dash. Then current through R3 is a then I3 double dash. So this is the current values of the source 2 is acting alone. So after this one, what we need to do means, so we need to add the response of the each and every source. I mean the current through the first element, that is the first R1 element. So we have given on the name as, so that is I1, means current to flows through the. So current to flows in R1, that is I1 equal to, so I1 dash plus I1 double dash. That is a combination of the two responses. The theorem is only saying us that is response of any one of the element equal to the algebraic sum of the responses given by the individual sources. So that we need to consider the response of this particular element value equal to the, so response given by the V1 and also response given by the V2. So that is summation of those two is which one, the overall response of the first element. So here the source 1 is so giving the current towards the, so that is the left to the right side, and the source 2 current is giving the current from the right to the left side. So that, so the different the total current flows through the R1 resistor is which one? So it's a difference of the, so two responses. Then coming to the second one, so similar to that, current flows through the R2, current flows through R2 resistor. So that standard notation we have given the name as I2 equal to, so the I2 equal to, it is a I2 dash plus I2 double dash. So algebraic sum of the responses given by independent, each and every independent source. So that we got the I2 dash plus then combination of the I2 double dash. So the I2 dash value, so it is coming from the source 1, that is top to bottom, and here coming from the source 2 also top to bottom, both are addition. So the resultant current through the R2 resistor is so that is a combination of the two sources, means combination of the source 1 response and also the source 2 response, that is I2 dash plus I2 double dash. So this is current flows through the R2 element. So this is the current flows through the R1 element. The last one, current flows through the R3 element. So that is I3 equal to, same the combination of, so response given by the first source and also response given by the second source. Why should I kept a minus means the source 1, when we connect to the, when we apply the source 1, then the corresponding response move towards the R3 is the which one, that is the left to right. Again it is this like this direction. So coming to this one, so it is like this direction, both are opposing. That's why the resultant value should be so difference of those two, that is I3 equal to I3 dash mean I3 dash minus I3 double dash. So this is the responses given by the each and every element. So this is the way to get the superposition theorem. By using the superposition theorem, we need to get the current each and every resistor. So when the multiple number of sources are present. So in the explanation, so what we have done means, so take an example. So this example circuit having the two sources, that is the voltage source 1 and the voltage source 2. So how can we apply the superposition theorem to this kind of source means, first we need to connect to the source 1. I mean source 1 is acting alone and the source 2 can be disconnected. I mean this source we need to connect alone and the corresponding remaining source can be disconnected. If it is the other source also present in the network means, so more than two element, I mean more than two sources also present in the network, we can simply so disconnect those remaining sources. So in this case, step number 1, we need to connect to the source 1. I mean, so they apply the source number 1 and the remaining sources are disconnected. If it is a voltage source, we can simply short circuit. If it is a current source, we can simply open circuit. So in the network, we have the voltage sources both. So that we need to disconnect the second voltage source and which can simply replace it by the short circuit path. Then the corresponding current values are, so this is I total dash, I1 dash, then I2 dash, then also the I3 dash. So current through this element is I1 and I2, then also I3. So here the I1 current, the current flows to the first element is I1 and the current flows to the second element is I2 and the current flows to this element is the I3. So while connecting the source number 1, we need to take the I1 dash, this one is I1 dash, then this one is I2 dash and this one is the I3 dash. So corresponding resultant values of I1 dash, I2 dash, then also I3 dash. Then step number 2, so what we need to do means here need to take the source 1 is source 2 is acting alone and source 1 can be disconnected. So while connecting the source number 2, the corresponding current values are, this is the I3, we have given the name. So this is the I2 and this is the I1. So the corresponding current values are I3 double dash, I2 double dash and also the I1 double dash. So first we got the values of I3 double dash, that is equivalent to the total current of the circuit. That's why we got the I3 double dash equal to I total double dash. And the remaining one we can apply the current division rule, will get the current through the each and every resistor. So based on that, we got the I2 double dash value and also the I1 double dash value. So this is I1 double dash value. Because current through, so R1 element, this is the current through R2 element. That's why I1 double dash we have given the name as I1 double dash. So this is the current through R1 and also current through R2. So all values are we got while connecting the source number 2. After that, step number 3, we need to get the so response of each and every element, means we need to add the so responses given by the individual sources. That is, so response given by the first source and also response given by second source. If it is a presence of the third source, also we can add the so one more response given by the other source. So that we will get the again combination of the I1 triple dash, like I2 triple dash, then I3 triple dash. So this is the superposition theorem explanation. Now, what kind of steps to involved in the superposition theorem means? So that is already we have discussed in the previous slide. So that is, so let us consider a network. So that the network having the two or more than two independent sources, we can simply apply the superposition theorem to get the response of any element. So first we need to take in the step number 1, we need to consider the only one source. If it is a current source, okay, no problem, we can consider. If it is a voltage source, also we can consider. The remaining all other sources can be disconnected. If it is a voltage source present in the network, we can simply short circuit. If it is a current source present in the network, we can simply open circuit. That is, terminals should be open. And calculate the corresponding current and required parameter value, that is current or voltage values based on the requirement. So that is the step number 1. And step number 2, that is repeat the above step, means so need to disconnect the previous source and also all other sources in the network and connect to the second source. And also similarly repeat the third step. If it is a presence of the one more source in the network, we can also take the so step number 3, that is repeat the again same step only. And the last one is need to determine the current through each and every element or each and every branch. So that is algebraic sum of the current given by the each and every element. So if it is a so source 1 given something value is I1 dash, and also the source number 2 is given the current is I1 double dash. So the resultant value of the R1 element, that is I1, equal to combination of these two, means I1 dash plus I1 double dash. So like this we can add in the step number 3, means we can determine the whole response of the individual element. So that is algebraic sum of the both responses given by the each and every. So that is in the step number 3. So these many steps involved to apply the superposition theorem for any kind of the circuits or any kind of complex networks. So summary of in this session means, so till now we discussed about the superposition theorem. What is superposition theorem and the statement of the superposition theorem. The superposition theorem is purely applicable for any kind of complex circuits. So consisting of the two or more than two independent sources present in the network. So that is only the thing we need to apply the superposition theorem. And next after that what we have done means, so how to apply the superposition theorem to the networks. That is explanation about the superposition theorem. I mean the same step already we have done, that is, so first we need to take a network, simple network having the two or more than two independent sources. If it is a two source network, first we can connect the one source acting alone, and the rest of other sources can be disconnected, and which can be simply replaced by so their internal resistance. So then after that then how can we get the whole response of the each and every element. So that is also we have covered in the earlier slide. And after this one we need to discuss about the applications of the superposition theorem. Applications. So application means, so here this these superposition theorems are used in so network having the multiple AC sources with a different frequency. So network having the multiple AC sources, so with a different frequency. This is the first application. And the second application of the superposition theorem is, so it is used to design the two-port network. So we need to design the two-port network by using so superposition theorem. That is the base only we need to design a two-port network. So these kinds of techniques are used in the power system like that. And also we need to apply this kind of superposition theorem for BJT circuit design. I mean in electronics, so we can use it to designing of so bipolar junction transistors. So also we can use, and also by using the superposition theorem we can analyze the, and also we can going to make the operational amplifiers. So these are the so applications of the so superposition theorem. So this is the end of the session. So till now we have discussed about the superposition theorem statement, what is superposition theorem, so what is the purpose of superposition theorem, and the statement, and also the explanation. I mean what kind of steps are involved to apply the superposition theorem, and after that so what kind of procedures to get the response of any element by using this theorem, and also the applications. So these many applications are there for superposition theorem. So this is the end of the session. Thank you one and all. In the next session we need to discuss about the so numerical based on the superposition theorem. Thank you.